Good afternoon. It's that time again to get started and talk about the exam that's coming. And maybe talk a little bit about COVID-19 since I've been getting a bunch of emails on that. The faculty have. You guys haven't gotten as much, but things are happening in the background. And if you read the news, you know that other universities are doing things, and we have plans here, apparently. That's what I've been told.
Thursday, no school?
No, the best estimation, I mean, no school. A little side note is my dean has told me that universities are the only place where people pay money and are happy to not attend class.
Yeah, right?
You know what I'm saying? I mean, if you were doing anything else and you paid money for it, you'd say, I want my money's worth. But at any rate, I think the best that what I've learned so far, besides reading some ASEE news, which is American Society of Engineering Educators, which I get every day, and I forwarded that to my fellow faculty members because it talked about all the schools and what they're doing within the engineering camps right now. Our provost, though, wrote us yesterday saying, well, maybe this and maybe that. And of course, we don't really know, right? He said, be prepared. It could happen really fast. So being prepared is we will switch from doing what we're doing right here to switch to some online thing.
I think that'll end up about the same.
For me, because of the way I teach, I mean, my graduate student in California, he had to demo his real-time DSP. I did a FaceTime with him for about 45 minutes, whereas last night, the students that are in class had to do their demos. So I've been practicing at that with him, and the only thing that's the fly in the ointment or whatever is the infrastructure. And there was an article on that I saw today too, that if campuses switch to that, their infrastructure for videos and streaming and other one-on-one things could get taxed and start crumbling. Since I don't use Canvas, I won't know what Canvas will be able to support or not support because I don't plan on switching to it unless it becomes essential. But we'll just see how it plays out. So just the numbers that were thrown out yesterday but may change was within the next 2 weeks. And then he sees the possibility of a 4-week outage where nothing will happen. I mean, it'll be this online some kind of thing. But it's anybody's guess, right?
How many cases of COVID in Colorado now?
8 or 9? Is it 12? Okay. I just found out before I came down here because I play music in retirement centers, and guess what? I've been figuring last Tuesday night that they wouldn't let us in. They did. But the place I play at tonight, I've got to go through screening before I can get in and answer a bunch of questions, which I think is just fine. I mean, I could walk right in and I could, any of us that play in the band could really mess things up. And
Well, somebody was telling me today that a lot of folks will be carriers and never even get sick, but they'll infect a bunch of people.
yeah, and
because they're not susceptible.
it could be me too. I don't know. I mean, I'm just saying that, and you guys would say that too, right? We don't know.
Oh, I know.
I'm not going to touch my face. They're old people.
Yeah.
Unless you really want to go out with a bang.
Well, I have a mother-in-law that's 87, and my brother-in-law on Sunday, because we're up there every Sunday, we bring her dinner and we hang out with her. My wife plays games with her. And my brother-in-law said to my son, who works kind of in janitorial and cleaning type stuff, you're going to wear your gloves this week? Are you going to make sure you're safe and sanitary? Because you don't want to get your mom infected, who will infect her mother, and then her grandmother will probably get sick and not survive. He never said anything to me. It's like, don't you realize that I'm also in front of people all the time too? He's a work-at-home kind of guy, so he knows that he doesn't really have that sort of same risk. But at any rate, we're going to review for the exam. I'm going to go through like the quiz, which the solutions are up there. I've also pushed out Project 1, so I want to get that introduced to you so you can start thinking about doing work on it. It's an ideal thing to be working on at home if we end up having to be at home, and it will be due after spring break. I'm really putting on a big push right now in all 3 of my classes to try to get stuff out there for spring break and just do it. And that's kind of the reason why I'm not doing my other self-evaluation and all, writing up all that stuff, because I'm saying I got to get this stuff pushed out, plus the interview candidates that we have coming in too. So I guess I could start lecturing on stuff we left off with, but that's not really relevant. Probably the most important thing is to look at the exam. So let's start with something that I think would be a good thing to start with, and that would be this. I didn't put this out so I can draw on it, but at least I can look at it here. Because I actually, you know, I could take this quiz and I could convert this into some exam problems just like that. And maybe I should do that, I don't know, and just take a total another run on it. You guys would probably say, fine, change the numbers, let's see if we can do it for real. Give me some feedback so I can be pondering this over the next day, because I haven't put the exam together yet.
Yeah.
Is that intriguing in any way, shape, or form? No?
No.
I may have scored something wrong too,
Yes.
but okay. Bring that up to me afterwards and we'll fix it. Or come to my office. I was in a hurry to try to get it done, as Colton knows, because
I was asking homework.
Yeah.
The homework
I dashed in on my bike because I was at home since I had PT, which today was a hard day of PT. They really made me work pretty hard, and I'm feeling kind of wiped out on half of my body, or a quarter of my body. So what a lot of people missed on this quiz, and since I've just graded it, you missed, about half of you didn't notice that there's a sync function here because there's a rectangular spectrum.
Yeah, it was kind of backwards.
Yeah,
It's a square in the frequency domain, not a square in the
Yeah.
time domain.
it's all fair though, right?
Yeah, because it's flipped swap.
Yeah.
It just when I was looking at the exam, I was like, oh shoot, I can do that.
Yeah, and the fact of the matter is, remember I've said multiple times now, we use simple spectral shapes, simple filter responses like ideal brick wall filters and things just to make the modeling easier. So in this case, the spectral footprint is this nice rectangle. And yeah, you could say what is it going to be in the time domain? So it's an inverse Fourier transform, so it's going to be a sync. And like I said, I can't draw on this. Another thing that went unnoticed is the fact that that's in megahertz. So I tried to be more realistic about things. I labeled things in megahertz in here, but then the numbers I had to put the real values in megahertz or microseconds, whatever the case may be. So the carrier frequency is obviously at 70 megahertz, and you know, this term right here, pretty much everybody had that unless you missed the megahertz part, which some of you did. So trust me, I'm going to do this kind of thing on a problem. I'm going to make sure you have to pay attention to the units too, because it just seems like the way I should approach this. Then in terms of figuring out the scaling, you have a 5 over here, but you know that things split in half, right? When we go through the modulation operation, which is double sideband, we're going to split that. So that 5 had to come from a 10, correct? So we know there's a 10 there, but then we have to look at our rectangle and say there's a 2 in there, and actually I think I do have a mistake in here now that I'm looking at it. So I graded everybody's paper wrong. This is actually 2 megahertz, so this should be 2 megahertz as well, I'm pretty sure. I'll check on this though. Pardon me? The scaling would say that should have to be 2 megahertz if I want to keep the units correct, and I have to keep the units in hertz or seconds or whatever. So I think this 2 should be 2 times 10 to the 6th, just like it is over here. I get confused on this because I get in a hurry and I just want to get the basic idea down, but then figuring out the exact units, I have to think about it. And I have to kind of think, does that make sense to have such a huge amplitude in there? And I think that it does because the width of the spectrum is small in the time domain. In other words, the sinc function is very compressed in time because it's got a 2 times 10 to the 6 in the argument, so it starts rippling off really rapidly. So I'll have to make sure I change this. So there should be a 2 times 10 to the 6 in there, I believe, and that's from the sinc function. Because up over here, this is actually 2 times 10 to the 6th, right? Everybody see why I'm saying this? And this 70 is 70 times 10 to the 6th.
Yeah.
Good? So that's missing. That's my mistake. I'm not regrading the quizzes. I'm just saying if we do this on the exam, anything like this, you got to watch all the units, make sure you catch them all. And then finally, the message signal is everything less the carrier. So when I take into account that too, which I didn't do properly, it should be 20 times 10 to the 6th sinc of 2 times 10 to the 6th t for the message signal. The 2 from the sinc, but then the times 10 to the 6th is what I forgot about. Any questions on that? Will I use a sinc function in a rectangle? I don't know. I'm going to try to make the exam as glitch-free as possible, so I'm not going to make extra little nuanced kind of details all over the place because that'll just bog you down and make it harder for you to do the exam. So I'll think about that. Do I really need to do that? I mean, obviously I could have made this problem a whole lot easier by just simply scratching that megahertz away, right, and just make it be hertz. Then it would have flown along without as much care or concern. But some of you are in the lab, and in the lab everything is real frequency, so it would kind of make you feel like you're not seeing as much realism as possible. Okay, part B is demodulation, so it's at 70 megahertz, so we need to multiply by a coherent carrier at 70 megahertz. So 70 megahertz was part of the answer. Nominally, the phase angle should be 0 because the carrier was modeled here as being at 0, so that's true. How do I make that go back up again? And then the bandwidth is what is the low-pass bandwidth. So when we translate this down to baseband, which is what happens when you multiply by that carrier C of t, everything is now centered on DC, so the spectrum is 1 megahertz above DC and 1 megahertz below. So the low-pass filter bandwidth is what we talk about down here when it says select a reasonable low-pass filter bandwidth. So that should be 1 megahertz or greater.
But less than 60.
Less than 6, actually less than double frequency, right? We get double the frequency in the coherent demodulator. So we're going to get something up at 140, so 139. Does that make sense?
Yeah.
Okay. Thank you for bringing that up, because now I can ask you that question. I can say it has to be greater than, but it absolutely has to be less than what I just said. Sorry about that. But you, again, in the lab, you've seen all that, and you kind of you have a better appreciation for that. And what that
Yeah, I guess my real question with that one is what do you, I know it's good practice, but it's so far out. Do we even care?
Not a whole lot, no.
Because it's not like it's what's getting transmitted; it's what's
Right.
in your computer.
I think in the lab, don't I have you use that 1 megahertz low-pass
so
filter,
like
the double frequency, and that's a 6th order, if I'm remembering right, or is it 7th order? It's pretty high order. Count the number of reactive elements.
All I know is it's BPF.
Well, there's BPFs on there too, but this is the LPF.
Oh, the okay.
And those of you in the lab, that works really well. Even though it doesn't match the design frequency, it gets rid of that double frequency.
Yeah, that's like way out of
Par excellence, right? It's gone. You see just what you wanted to see.
Yeah, you just go really far out, you can see it. But it's, I'm guessing it's just good practice. Just
Yeah.
make sure you're getting rid of
The
it.
fact of the matter is, what we care about is how many dB down is the double frequency going to be? Because it's never going to be 0. Never, ever will it be 0. It's always going to be just so many dB down, because that low-pass filter rolls down. It has the skirt, as it's referred to as. And that's going to be so many dB down, way, way out there. OK, so that's the answer. Then the other piece we talked about, if phi happens to be pi, then we're going to end up with a cosine of phi in there, and that's going to invert everything. And the question is it bad or not? If it's audio, it's probably not going to be bad. If it's data, it would be inverted data, and there'd probably be an ambiguity resolver or something in the framing that would be looking for a preamble, starter frame delimiter, and it would say, I'm looking for this frame of bits. I didn't see this frame of bits, but I saw the complement of those frame of bits. And oh, so it came in inverted. I'll just flip all the bits over. Everybody following what I'm saying? I'm not teaching the details of digital comm, but with digital comm, you just have to kind of say, OK, I can do things like that. You can have patterns embedded, and a starter frame delimiter is kind of a standard terminology in packet communications. They also use other things in digital comm. It's called a preamble, which would be another set of digits that would allow the coherent carrier, if it was a digital system that needed to get locked, the preamble would be a nice simple pattern of all zeros or all ones, something that a phase lock loop would lock onto very rapidly, and then it could coherently demodulate from there. So those types of things are used also in digital comm. Okay, AM signal is the next one. So here I gave you the message signal, and this was kind of the problem that I alluded to last Tuesday, saying that if you have two sinusoids, it's got to be pretty obvious what the minimum value of the message signal is, unless things are rigged up in a particular fashion. And here, you know that the minimum value of the input is going to be minus 12, right? You know, it can be no lower than that. But in fact, you know that it is exactly that, because if you put in t is equal to 0 in this first term, you get cosine of minus pi, which is minus 10. And if you put t is equal to 0 in the second term, you get minus 2. So you're going to get minus 12, right? You see that? And I had Python make a picture for me. You can see, sure enough, it is minus 12. The peak, however, is not plus 12 in this case. It works out to be something different. But for normalizing the message, you care about what the minimum value is. So this was a special scenario.
Can you say that one more time? So why it's 12, not just 10?
Well, this is swinging up and down by 10. This is swinging up and down by 2. So the worst case scenario, the most negative value you could swing to would be minus 12. And you can't predict it exactly because the phasing in here might not make that actually be achievable. But in this case, because when t is equal to 0, I get cosine of minus pi, which is the same as cosine of pi. It's minus 1. And then over here, I get cosine of 0, which is 1. So I know from inspecting the sum of these two cosines that at t is equal to 0, I am right at minus 12. That was really the bottom line.
But it has a phase, so one of them is
Yeah, but that phase works to your advantage. When t is equal to 0, you get cosine of minus pi, which is minus 1. And this has already got the minus sign.
Okay, I didn't notice that.
Yeah, that was my problem design nuance. Just trying to make life easier, but that's why I hinted at that last Tuesday. So that's good, minus 12. So that tells you what you have to normalize by. You have to normalize by minus 12, the message. And then when you drop down, and I kind of worked it out in here also, then you drop down to part B, it's trying to find the power in the sidebands. So pretty much everybody wrote down this equation, but how to work with it was another matter. You have a squared, ac squared, which is 100 squared. You have a squared, which is 1/4. And then you have the 1/2, because you have the cosine from the cosine of the carrier term brings in that extra 1/2. Now you have to find the power in the normalized message. And the normalized message is, because these two sinusoids are at two different frequencies, we can find the power in this message signal plus the power in this message signal, because they're not at the same frequency, and that's just a squared over 2 for each of them. So that's going to be 10 squared over 2, 2 squared over 2, but then because we're normalizing the message by 12, and that was talked about up in here, you can just factor that out. That 12 factors out as a square, so it's down there in the denominator as a 12 squared. Good? It is tedious, right?
I wasn't expecting the 112 right at the end.
Yeah.
Or 112.
That's why you had to get that, though, in part A. Whether I would repeat this problem like this, I might give you a normalized message and still give you a calculation for the power in the sidebands. I might say also calculate the power in the carrier and then get the efficiency, which would be the ratio of the power in the sidebands to the total power, right? So there's going to be something on that for sure, rolled up into a problem. So that'll happen. And I worked through these numbers, so I get 451.39 watts. So this is golden material for the exam. So make sure you review through this or just look at the problems you've already worked in the homework. And I'll get the solutions posted up if I can before I leave to go play in the band. But I've got them all set to go on my desktop. I just haven't put a password on them yet. But
So the edge of the exam material was the homework we just did with Hilbert transforms
Yeah.
and analytic signals?
yeah, I want to get back over to that. I wanted to just go through this first since it was
Okay.
fresh in my mind.
So the study material, the things we should study for the exam is just the notes from chapter 2 and up through chapter 3, the first 6 quizzes, and the old exams you posted.
Yep.
Okay, that's fair.
So I'm looking in chapter 3 right now, so we're stopping right where I put those red lines from last time,
Okay.
above that. And then back in chapter 2, it's the things that I did. So I'm prepared to walk through that if you want me to right now. I'd also like to just look at some of the old exams and see if anybody has any questions from those. I'd like to talk about the project, and then I'd like to also talk about superheterodyne. So I'm probably going to do it in that kind of order. I'll talk about old exams, talk about walking through stuff, and then I want to go off and talk about the project. And you're working on superheterodyne radios tomorrow in the lab, right?
I haven't looked at the lab yet.
Yeah, that's what you're doing. It should be like one of the most pleasant labs, except for the latter part when you're going to try to send data through a link and then feed it back through Pi Audio Helper in a Jupyter Notebook. It's kind of a cool thing. It's a bit air rate, digital comms kind of a thing. But the radios are really fun to work with. It's all analog IC stuff, RFIC stuff that I developed, and then Professor T. Camp did the PCB designs for me, and we sent them off to Spectrum Laser, the place in the river bottom over here, to fab them. And they're fun, I think. You get to receive real signals and listen to them and set the local oscillator and learn about that stuff. So what do you want me to do first? It's either cover the material, which I'm not sure I really need to do that, but I can, or look at the old exams, which is more of a... Okay.
Old exams is a 2 in 1.
Okay. So before I forget, what you can bring to the exam will be your crib sheet that you've been using, a 2-sided sheet of your own material, which I'll just ask you to attach to your exam when you turn it in, just so I'll look at it if there's something funky, like maybe you wrote down something bad and it just got you all messed up, but you'll get it back again though. And your calculator. Sound okay? Bring the best calculator that you own. I'm not saying that facetiously. I want you to bring the tools that you know how to use. Don't bring like a TI Inspire or something that you've never used in your life.
I like my TI.
Don't bring a slide rule that you've never used in your life or something crazy like that. It doesn't require batteries though, but it requires knowledge of how to use it. So.
This thing is the best $80 I ever spent.
And what brand?
Just TI Inspire.
Okay.
I don't know, Texas Instruments.
Yeah.
Did you get the cast one?
No, because they checked for that back in high school. So I have the CX that no algebra system, so I can't solve integrals with it.
Yeah.
Yeah, I got this gas one.
I bought the CAS one. My sons went to school at Colorado Springs Christian, and they had to have it, right? And you had to have it too.
I had this for like 6 years.
Yeah.
Oh, really?
Yeah.
Oh, wait, yeah. I got mine junior year of high school.
Yeah, that works just fine.
Yeah, they were super strict about AP tests and algebra systems because they realized you could just bullshit through the whole test with it.
Just put it
And I see it when I grade papers. I see it in this class and other classes, but I also see where it kind of messes somebody up. So that's why I bought one, because I wanted to understand what was going on with them.
Nice, aren't they?
They're pretty nice. I have the software on my iPad too. It's available for the
Yeah,
iPad
I've
as well.
seen teachers do that. It's so weird. I don't know where you guys get that.
What?
Just the emulated OS.
Oh, for the iPad?
No.
Oh, there's an app that runs on your PC. It comes with a calculator.
Well, I lost that in work. That sucks.
You got that when you bought it, and then you could download it from the TI website. And then you got one license key that you could use it to install on a computer.
Really?
At least that's what I got. Okay, so old exams. We'll start with this one. So this just takes us back to review of Fourier series. So I asked a pretty fundamental question in here. I asked the type of question that you'd probably be asked when you were taking 2610. Here's a waveform. It looks kind of funky, but the idea is to just, do you know how to work with Fourier series coefficient calculation? So it was just doing an integral and finding the average value. So this problem just came down to finding the average value of the waveform, or the DC value of the waveform. Have I ever used this problem again? I don't recall. I don't think I've ever looked at it again, but that's all this was. And then finding the average power is the same thing. It's not finding Fourier coefficients, it's just taking the integral squared. And I picked something that requires calculus, but it's not hard calculus, because e to the something is a familiar function to integrate, right? There's no partial integration by parts or anything like that. So that's what I did for that one. Basic theorem type stuff, Rayleigh's energy theorem. So this is a problem that I may or may not have assigned in the book, but it's the idea that if you have an aperiodic signal, you want to find the energy, you can work either in the time domain or the frequency domain. And in this case, integrating the sinc function is totally crazy. It's magnitude of 2 sinc 4t squared is just going to be an impossible integral. But if you're thinking, I have Fourier transforms available, just Fourier transform it, and it's a rectangle function, so that calculation works out pretty easily. This problem is just a review of linear time invariant systems. This was a simple multipath channel where signal arrives at the receiver having gone through a delay of 8 seconds or a delay of 4 seconds. And so I wanted the Fourier transform of that impulse response. So you Fourier transform term by term. I should probably download these, but I'll just try to get by like this. So you'd Fourier transform that. You get the two exponentials. Time delay gives you a phase shift factor in the frequency domain. And then factoring that out, and I expect you to be able to do a trick where you have to do factoring to get either a sine or a cosine, because that shows up pretty frequently. So I factor out to get a balance there. In this case, there's a plus sign in between, so you know you're going to get what? When you factor, you're trying to get the two terms to be equal and opposite in sign, but if there's a plus sign in between, what does that form then? A cosine. So if I gave you a problem like this and I put a minus sign in there, then you'd be getting a sine, right? So you just one way or the other. So here you get the cosine, and you get a phase shift factor out in front of the cosine. And the main thing that this problem was looking for is not, well, once you work part A, you get h of f, but in part B, you're looking at what is the cosine of 4 pi f going to do. It's the magnitude response of the channel that the communication signal goes through, and a communications engineer would be pretty distraught if the null, due to the multipath, occurs right at the center of the channel. You know, suppose your signal is being sent right at that frequency. So what are you doing? Think back to physics. You're doing what type of interference? CO or DE?
Destructive or destructive?
Pardon me?
I think D.
Destructive, right?
Find or D.
CO is constructive, right? So you'd be destructively interfering. Most communications channels, like LTE, for example, does use modulation scheme where there can be ripples in the frequency response, and they can affect the way the LTE scheme works, but it divides it up into small little subbands, and if one subband is getting a deep null in it due to multipath because of where you're standing when you're talking, which you don't control, right? It'll work around that null. It'll manage that with coding theory, and it will recognize that that particular subband is suffering right now because you're in a null, a channel null. And those, what do you think? Do they change or do they stay the same?
Same frequency, same rate.
If you move around, though, two rays could be arriving at you from two different paths, and the time delays are going to change. So. Okay, so that's that. This is just a Fourier transform, kind of a problem, but this rolls inside of it the analytic signal idea. So this is very similar to the second part of the last homework problem that you just turned in, right? Does it look familiar? So I think that's why Dr. Zemer had it in there.
There's no like scalars, it's just saying it's 1 and 1.
Yeah, exactly.
And linear shifted by FC.
So you already know that if you just take x of t plus j x hat of t, that is the analytic signal, and that takes your two-sided spectrum, which would be like this, and makes it just the positive side, right? It's just going to be the triangle on the positive side, but now you're going to shift it up in frequency. So that's what'll happen in this case. And then if you go through the math, you get a doubling in there too, because the positive frequency combines to give you a factor of 2, and on the negative side you get 0, so you get twice on the positive side. So I'm looking at this and I'm saying, did I make a mistake here? It should only be the positive frequency, so why do I have the negative frequencies in there? I guess I'll put a disclaimer up. Sometimes my solutions have errors in them that I never went back to fix. In other words, I fixed them when I graded. I think this has got an error in it, though, because I think it shifted up in frequency to the carrier frequency, or maybe I'm not reading my problem correctly. Oh, never mind. I'm forgetting that I've got a bandpass signal up here, so
Yeah, that's
it's right. I was thinking of the homework problems, what I was winding back to. So the analytic signal wipes out what's on this side, right? That's gone, so we're just left with this. And then the e to the minus j 2 pi f brings it down, brings this spectrum that's here, brings it down to be centered on 0, and that's what that is. So that's correct. Anybody have a question on that?
X hat was that for? X hat.
The x hat is the Hilbert transform, and the way we get that is by taking j signum of f, or minus j signum of f times x of f. Actually, there's a problem with phase lock loops, a simulation problem that's going to run real time in Pi Audio Helper that does exactly this with a Hilbert transforming digital filter, and the idea is to down convert it to baseband. So this is a scenario that plays out in some software-defined radio front ends. Okay, this one, This is an AM type problem, so this returns us back to the quiz we were looking at. To find the modulation index, what you want to be able to do is you want to be able to get the modulation, which you see here, plus the pure carrier. You want to factor it so that you get a 1 sitting where that 10 is. So I pull out the 10, and then I have a single cosine, so I can immediately just stare at that and say, that's the modulation index, right? It's 8/10. It's just jumping right off the page at you. Why? Because the message is normalized already to have unit minimum value. So A is 0.8. And then to take this one through the analysis of the power in the sidebands, there's a couple different ways you could do it. You could go back to the formula we were looking at earlier for the quiz, or in this case, I chose to just take the sideband only term, like I've got written down right here, and just multiply it out using the trig identities. So I'll have the upper sideband and the lower sideband. And then I'll get the power in the upper sideband and the power in the lower sideband and add those two together, and that's the power in the sidebands. So that's one approach. Do you want to just refresh our memory how you would do it the other way? I can't draw on this, but I could draw on the whiteboard. Well, maybe I can't because there aren't any pens here. I guess you have to bring your own pens. They're over there. I can go off to the side, though. Let me just keep it on my electronic stuff. Is that a good thing to do, to just give that a try? So I would take 10 times 1 plus 0.8 and so on. I got excited and it wasn't writing in real time. It's still not writing in real time. It's doing really badly. I'm upset because I can't make it do what I want it to do. It's like it's freaking out. I've never seen that happen before.
It's usually when the software isn't able to cope in with that kind of response.
Yeah, it's probably because I haven't been using this, so it's trying to get it cached into RAM from memory or from somewhere. You don't know, but it's lagging way behind me by about 5 seconds or so. It's a new way of drawing, though, where you don't get to see what you drew on the pad and for about 5 seconds after you did it. So if this was our transmitted signal, if we wanted to get P sideband, it's getting a little bit better, but not much better. The formula says we're going to take AC squared over 2, and then the next term we have to include is the modulation index squared, right? A squared. So that's going to be I drew it, but it's not actually going to draw it. Oh, come on. And then what's the last term I need? I need the power in the message. And the normalized message is the cosine omega m, so what's the power in cosine omega m? 1 squared divided by 2, right?
Oh, the separate divided by 2? Or is it
Yeah.
not 1,
No, it's like that.
2? So why is the 0.8 not divided by 2?
That's the modulation index squared.
Little a, got it.
So we have 100 over 4 which is 25. Then 0.8 squared is 0.64, is that right?
Are you sure that's not 50? 100 divided by 2 is 50.
100 divided by 4,
Oh,
Is
that in
25.
parentheses?
yeah.
Okay.
Is this the answer that I have over here? That's what I'm looking for. 16. So I'll bring up my Jupyter Qt console. 25 times 0.64. Oops. We can write it down right. I can't write it down right. Dot. Oh, 0.64. So 16. So that's correct.
So just to clarify, it is parentheses 10 divided by 2 squared? Or is it 10 squared divided by
10 squared divided by 2.
2? Oh, you just accounted for, oh.
That's AC squared over 2, right?
Yeah.
And then I have A squared. And then I have to have the power in the message. And here the power in the message is easy because it's just a single cosine. So it's amplitude 1 squared divided by 2. So that's just the other way of getting there. Whereas what I did in that solution was get it individually, the individual upper and lower sideband terms. When you're studying, though, it doesn't hurt to say, I have a fork in the road. I could go that way. I could go that way. And if you have the time on your hands, just take both paths and see you get the same answer, because that will just sort of build your robustness in solving the problem. If you get a different answer, then you're going to be in a quandary, right? And hopefully you'll see the mistake. Or simulate it in Python and use the variance function, var, around a long vector of samples, and it will give you the power pretty easily too. I could always do something like that. I could this is just another environment. This is just the straight console, which is kind of like what you'd have in MATLAB. So I'll put up 10 cycles, and I'll say we've got A, which was 10, times 0.8 times cosine of 2 times pi times t. And then we have to put in a cosine carrier in here, cosine of 2 times pi times, let me just say 20 hertz relative to 1 hertz over there, times t. Oops, I didn't want to do that. I wanted to put a didn't need a semicolon. What I needed to do was put an x there. So just clear that away. So I have that, and then use the statistical operator variance and just take that waveform and just have it compute the variance will be the power in the signal in this case. Does that seem too amazing? I have to get in prop and stats to talk about that, but variance can be used for power. Standard deviation would be the square root of that, so STD. And then if I wanted to do mean, that'd be the average value, and it should be 0, right? And it's pretty tiny, so. Okay, so power in the carrier in this case is really simple, 50 watts. It's just AC squared over 2. Then drawing the spectrum, two-sided spectrum, you're going to have the power spectral density is going to put 25 of those watts are going to be lumped at FC, and 25 of the 50 watts in the carrier is going to be at minus FC. So that's, remember, power spectral density is such that when you integrate it, you get back the power in the signal. So you can just look at this by inspection and say, okay, of the 50 watts in the carrier, 25 will be here and 25 will be there. Then you have to think a little bit harder about the power in the sidebands, but because I worked this in such a way that I found the power in the upper sideband to be 8 and the power in the lower sideband to be 8, just from the math that I went through here, I can say that, okay, half of that power is going to be in the positive frequency side and half is going to be in the negative frequency side. So of that 8, 4 is sitting up here above the carrier, 4 is sitting below the negative carrier, and then on the lower sideband there's 4 below the carrier on the positive side and 4 above on the negative side. So that all works out. If you integrate just the sidebands, you'll get 4 plus 4 plus 4 plus 4, which is 16, and that was what the calculation showed already. Here's the coherent D-mod, just looking at an imperfect demodulator. So there's a delta F thrown in here. The low-pass filter is already set up at W, just defined generically to be W, but it's stated that the message is less than W. So when you multiply through the trig identity, you're going to get a difference frequency at FM minus delta F, and then you're going to get the double frequency term. And the double frequency term is removed by the low-pass filter. The desired term is what passes through. And assuming the assumption here is that delta F is small compared to FM. Let's see. What else can I say about that? This is single sideband, so with single sideband you either have the upper or the lower. In this case it was the upper sideband. Remember when we listened to single sideband, we only heard the message when you had the wrong carrier, D-mod carrier, the message signal was either shifted up in frequency or shifted down. So it was either grumbly sounding or mousy sounding. But when we did the same wrong frequency with double sideband, then you get a shift up in the message superimposed with a shift down, and that was that uglier sounding thing, the harmonic dissonance sound of pitches kind of colliding with each other from the overlay. It's a good question for me to ask you, though, if I gave you this problem with double sideband and said, so if you're listening to this tone at 1 kilohertz and there was a frequency error of 10 hertz, let's say, in the coherent D-mod, you would get out of the coherent D-mod 1000 minus 10, which would be 990, and then the sum would come out as 1010. So what would you be hearing? You'd hear the superposition of those two tones.
Yeah, it would sound not like harmonic, but like it'd basically be like how
A touch tone.
most things sound.
Yeah, or a little bit like a touch tone, because when you hit a keypad on a touch tone for a phone, that's 2 tones that you're hearing, right? You have the row frequencies and the column frequencies. But they're not at those frequencies. They are in that range, though. So I just said pitch shift. Advantages. bandwidth efficiency. Complexity, though, I want to get to the project before we leave here, and you're going to be building a Weaver DMOD for single sideband in software. So the DMOD is a lot more complicated for single sideband. This is not on our exam. This was frequency translation. So this problem doesn't apply to the exam. So you can scratch this number 8. Doesn't apply. And that's the end of that story. I'm going to try to go faster on this one. This was last year's exam, so this one opened up with just a simple theorem trying to relate the Fourier coefficients to a signal that's been differentiated. So if you send x of t through a differentiator, the idea is you just differentiate the Fourier series, and then when you bring that derivative operator inside the sum, it sees the e to the j n omega naught t, so it's popping that out, j n omega naught from the differentiation. And then you say, oh, if I plug that up in there, j n omega naught e to the j omega naught t, I've got x of n times that, and that must be what y of n is. So you've just established a theorem that says what are the Fourier coefficients of a signal that's been differentiated with respect to time. So it just pulls out a j n omega naught x of n. And that same kind of property is a Fourier transform theorem too, where you multiply by e to the j2 pi, or you multiply by j2 pi f when you differentiate. And that's in the table of Fourier transform. So this is just a version of that for Fourier series. This is just a Fourier transform kind of problem, finding the energy in the signal. So in this case, again, you want to work with the Rayleigh's energy theorem, work this in the frequency domain. So you've got the magnitude squared to work from. Only thing here is you've got to apply the filter. So you've got h of f sitting there, and then you have to find the Fourier transform of x of t. So that's two rect functions in the frequency domain. And then you just apply the low-pass filter to them, and that modifies the frequency shape. So the spectrum that has pi f over 2 doesn't get modified by this filter. The spectrum that has pi f over 6 extends, to plus and minus 3, but then the filter truncates it to plus and minus 2. So that's why I just rewrote 2/6 as 1/3, and then that becomes f over 2. And then those can combine together as 5/2 plus 1/3, quantity squared. And now you're going to integrate that over the rect function, which runs from -1 to +1. And it's an energy signal, so the units are in joules in a 1 ohm system. This is the theorem that I like a lot. I'll probably work this into the exam to have a problem that involves this theorem, which I think I said you could put on your crib sheet, right? Didn't you already add that?
I mean, the note.
Yeah. If you don't want to put it there, put it on your two-sided sheet. You can definitely have it, though. So this just involves identifying the period and then being able to Fourier transform the pieces of it, which in this case over one period is going to be a rect function in the time domain that's positive, and then a time-shifted rect shifted up to be centered on 3.5 and one shifted down to be centered on 3.5. And of course, those two terms are the second two terms here. So there you've got an e to the minus j minus an e to the plus j. So that's going to spin itself around into, no, never mind, you've got a minus sign on both of them. So that becomes a cosine with a minus sign out in front. And that's about as far as you can take that. I do ask you to find the power in the fundamental frequency, so that's just going to be finding what the spectral line is at the fundamental, and that's going to be when m is equal to, when m over 10 is equal to 1, so m is equal to 1, so it'll be at 1/10. Is that right? Let's see, what am I doing here? X of 1 over 10, that's going to be the fundamental, because the period is 10 seconds. So you just want to evaluate this guy when f is equal to 1/10. So plug in 1/10 for f, if you wanted to go that way with it, or just plug in m is equal to 1 inside of here. So that's, I get 1.04 watts. This was a problem that could use with a ruler, so have a ruler with you just in case I do something like this again, so you can find the rise time. So this was finding the 10 to 90% rise time in part B, but then it was just commenting on, is the system causal? And it's causal because what? The impulse response is 0 for t less than 0. That's a 3205 kind of a question. I'm willing to bet you saw that. And of course, this is the step response, but because the step response is related to the impulse response by the derivative, the same property holds about the step response being 0 for t less than 0. This is just going to the definition of the autocorrelation function. So I just wanted you to write out what the autocorrelation function would be from this sketch. So it's a signal that's on a pedestal of 1, and then it's a triangle centered on 0. And this has a units glitch in it. I've got things in microseconds. So you just have to get the units right in there. And the triangle, remember, the value down below here is half the base width. So that's 1 microsecond, right?
Tau would mean time delay.
In the case of the autocorrelation function, tau is used as the independent variable, though. So don't get them confused.
Just an arbitrary variable.
Yeah,
Okay.
that's a variable for autocorrelation. What's in the denominator, though, is half the base width of the triangle. And then you just Fourier transform that down below here, term by term, using the Fourier transform theory. So you're going to get a sinc squared function from the triangle piece, and then you're going to get a spike at DC due to that 1. And where did I don't know why I didn't put my units in the limits up here. I put that correctly, but I forgot to put 1 and 2 times 10 to the minus 6th. I screwed that up in my solution. And then this was an example of a nonlinear system. So I gave the response, the spectrum, and I said, what is the spectrum of y of f if you've got x of f plus 0.1 times x of f convolved with x of f, right? If you have x squared in the frequency domain, that will be x of f convolved with x of f, which will convert a rectangle into a triangle. So that's what I've got in here, and it's kind of the profile of a house. What's that called, Chris? When you look at the profile, that's not a dormer, but what is that you've got in a profile of a house? Since you do architectural drawings.
I don't know. Dormery comes out of the side of a house. It's just like a little perch. It's got that same shape, but
Yeah.
I don't do that kind of architectural stuff.
My brother-in-law draws house plans for custom homes, and he'd have a name for that, but I don't know what it is for sure. My son, maybe, who's the architect, would maybe tell me too, but it's a profile of something. It's a spectrum is what it really is.
Yeah, I don't know. I mean, just like it was that cross section, but
Yeah. Okay, here we have a double sideband signal, and I give you what the message is. And then I just say, design a DMOD for this, coherent DMOD for this. So the carrier is at 100 megahertz, so we need to put, you need to come up with what phi of t should be. So it's going to be 2 pi times 10 to the 8th is what I told you in the problem, plus some delta f. So I tell you that, and then I say you have to come up with what the low-pass filter bandwidth is, and then say that you'd probably want to choose W just slightly greater than the message bandwidth, which I guess I said the message, you get the message is a sinusoid at 10 kilohertz, so just greater than 10 kilohertz, so that if it gets shifted up above 10 kilohertz, it still passes through. Even though it has a frequency error on it, you still can recover the frequency shifted message. And then you apply that low-pass filter, and I use a notation that Dr. Zemer likes to use. LP just means low-pass part, throw away double frequency, keep low-pass. So we split it into the upshifted and downshifted frequencies, because this is double sideband with the frequency error, and this is where you have that harmonic issue of the shifted up and shifted down superimposing.
Should we move into the project?
I would like to, but are you getting tired of this?
No, just 14 minutes.
I know. I'm looking at the clock. There's a Hilbert transform problem. This is kind of similar to the homework problem. Are you guys feeling okay with this kind of stuff?
Some of it's unfamiliar, but I can go and look at the exams.
Okay.
I can review. It's perfect.
So realize that it won't be the same as any one of these, but it will be similar. I'm not going to do something really bizarre. If it's something very bizarre, I'm going to have to explain it very well so you can follow what I'm doing. I used to have a professor that I took circuits from. I took a bunch of classes from for my undergraduate degree, and he always said, he was Japanese, so he spoke with a pretty strong Japanese accent. He'd always say something like, I have to put a turn the corner problem on there. His idea of a turn the corner problem was, you've been driving along like this, I'm going to put a sharp turn in that. It's like you're going to have to turn the corner on that and go a little bit further around the current corner. And I don't really have a plan for that, but a little twist here or there might show up, so just be alert. It'll be a 5-page exam. That's the way I do it. So it'll be two problems per page. That's the way I set it up. It's a balance between having a lot of big problems. There might be one page that's all one problem, but too many problems gets you frustrated, but too few problems, then if you bomb one problem, then you don't do well either. So it's kind of, I have to pick a balance there. Okay, so I guess we won't get into super heterodyne because I do want to introduce a little bit on the project. So I'm going to go look at that, and there's a Jupyter notebook that goes with it. Just quickly back over to here. So project 1, and then the Jupyter notebook sample that goes with it, which I would like to play in if possible. So let me just go see if I can get that opened up here.
Project 1, 2020 down at the bottom.
Yeah. Got too many old versions in here. So if we get a chance, we'll look at it in there. So first off, the ground rules are teams of 2.
There's only 4.
And my,
More of us that can team up.
that's right, I'm forcing your hand. So John, who's in California, is a graduate student. He'll work alone. We have one other graduate student, so he'll work alone. And the rest of you are in two twos, right? I didn't want to, if I would have made it 3, it would have been really hard. Ho Fong is, he'll probably look at it though. You share the load if you work in a team of 2.
You share the load or if it's a team of 4.
Yeah, but then you don't get as much done, so.
Oh, we get a lot.
Well,
Oh, fair.
I want you to work in teams of 2.
Dang it, I need a larger project quote from school.
So,
Oh, you'll have a senior design project. Don't you worry
You
about
be
that.
quiet, I'm trying to leverage here.
okay, so here's what you're going to be doing. You're going to be building a 3-user single sideband modulator setup, and that involves building the Weaver single sideband modulator in software, and then you'll send that over a channel, and then you'll receive it, and then you'll build a coherent demodulator, which will use a Magic Genie coherent demodulator to pull off the signals. But what's interesting is the signals are stacked pretty close to each other, so you'll have to be careful to make sure you design the bandpass filter that you see up here. And the tablet's pretty well hosed up right now. You'll have to make sure that when you go try to demodulate that signal, it won't pick up that as a lower sideband associated with the M1. If you do, you'll have scrambled sound coming out. It's good to at least mess that up, though, and see what happens with that. This is a very old technology concept that the telephone company used to use, but still it's a useful kind of investigation to play with interference and designing filters and things. So to build it up, you have a top-level simulation function, which I provide in the notebook. And then what you have to do with this top-level function is you call into the modulators 3 different times. And this is what the modulator looks like in standard continuous time block diagram form. This is the Weaver single sideband modulator, except you'll be implementing in digital signal processing using multi-rate signal processing. So you come in at 8 kilohertz, and then you go through an upsample by 12 to get it up at a 96 kilosample rate to go across the channel. And then you downsample later. So you'll have to implement this function, which I give you a lot of info on, talk about multi-rate processing, and then the coherent demodulator will consist of a low-pass filter to get back the image of interest, which is at baseband, and then this is at the output of a coherent demodulator. So this low-pass filter is the coherent demodulator's low-pass filter, but then you'll also downsample by 12 to get back down to 8 kilosamples. In general, the multi-rate is part of modern DSP, but in this class I've successfully had that work through, and you'll pretty much get a handle on it because I walk you through that in this reader. In terms of what the document has in, or the notebook has in it, I'm just going to fire it off here. It uses all of the audio files that I've shown you already. And rather than working this in real time with Pi Audio Helper, which Chris is exposed to last semester, but I'm not going to drag everybody through the mud on that because it's
a pain to set up.
It's a lot more DSP stuff than we really need to be doing in this class. So you'll be doing things like this, whatever operating system you have. And that just has noise on it. That's the British one.
Is that by default, or is that like?
No, that's just a quick example. I'm going to take you through the code example, though. So I have my solution in here already. So you have the same notebook, but you don't have this code module called COM1 Project 1 New. So I just loaded it, so I now have my solutions in here. And then here's the top level that I give you. The top level sets up the modulator to either test with noise or test with speech. And then by coding this M combo string, you can turn on all three carriers, which is what 111 means, or turn on the center carrier, which would be 010, and so on. So you can do your diagnostics. And because I'm running it in demo, I'm going to be running in demo mode, I'm going to set that equal to true. So then it produces the composite signal. You have to build the Weaver modulator function that this thing calls, like I said, 3 different times. So that's a helper function that you build. This is the spot to build it. I describe, where you start writing your code. You also have to build the coherent demodulator function, which I give you placeholder for that. So I'm going to run this. I'm going to put up all 3 signals with speech. And it's designing some filters in the background. And then I'm going to demodulate the carrier at 20 kilohertz, which if we go back up to the block diagram is way up here. It'd be this carrier right here. So when I set the transmitter up in this particular example, I said the carriers are at these 3 frequencies. In the tasks that you work on, you move them around and try moving them really close together to see what sort of impact that might have. So here I set it up with, got to get down here, the carriers are at 20, 24, and 28,000 hertz. So I'm going to demodulate the 20,000 guy, and that's what I'll do here. Designing some other filters inside of that to do its stuff. Here I can plot the spectrum at baseband of the recovered signal, and this is the spectrum of the 3 signals together. 20 kilohertz, right next to it is the 24, and then the 28. So those are the 3 message signals. But I'm demodulating the 20, so demodulating that guy. And if I go to play it back,
the little tales they tell are false.
so that comes back. If you listen really closely, or depending upon how you design your filters, you'll hear some background noisy things from the other signals. They'll be spectrally inverted and kind of flipped around, but just to let you know, if I put this at 24, I will demodulate the other speech signal. This will be the middle one.
Hoist the load to your left shoulder. Take the winding path to reach the lake. Note closely the size of the...
And then the third one up is the U.S. male. So there's a British male, a U.S. female, and a U.S. male.
Those are very tight.
Packed together.
Yeah.
Yeah. So you get to work on some filtering issues, and then you can make them even tighter if you want to. I mean, I could definitely hose it up by putting them literally on top of each other. Then you'll start hearing bad things. So as you work through this, you kind of have fun listening to things, and if you mess up, you'll know it. You test it with noise, though, in the very beginning. I have you just test with white noise, and then the spectral shapes are just rectangular blobs, and it's a lot easier. That's talked about in the reader document. That's over here. Use a noise spectrum, and then this is what it will look like with all 3 signals on, and this is what it looks like with just one on for particular filter configuration. You can see there is some leakage, but it's down quite a few dB, and it makes it kind of interesting because the filters are realizable as opposed to being an ideal filter. Question?
So as far as reporting on this, does it just demonstrate?
You will put everything into the Jupyter Notebook and then do a print out of that, and then that's what we turn in. And you also make some WAV files and send those in too. So I'll listen to the
So
WAV
a
files.
Little PDF and an audio file, like, is it
Yeah, exactly. And then I listen to that one. There's one part where you send in a couple of
That's okay with
zips.
me. You should do an in-class example at some point of how to export Jupyter Note from Jupyter Notebook
Yeah.
to PDF, because I have not found a good way to do it.
Oh,
I
You gotta
can't
go to Typora,
Typora is a good way to go.
export it to Markdown, and then open the Markdown.
I did that already. I actually have a video. I can point you at
Yeah,
that.
I did it like the second class. That's the best way to do it.
Okay, Typora.
He is a
Markdown to Typora.
he's a pro.
Yeah.
I mean, and I'm fanatical, which is why I get behind in my work. Nobody knows how fanatical I am except me
Oh,
and my
that's a pretty good
my
idea.
wife. My wife, who gets frustrated because I tend to complain a bunch. So, but nobody understands all the things I do. So, okay. So, we'll see you on Thursday. We're not interviewing anybody, so I don't have any reason to be dashing from one place to another like I was last Thursday.